Okay, so the next theorem is that if A is the generator of a semigroup, that's a zero semigroup TT, then the domain of A is dense in X and A is a closed operator. Okay, so let's see the proof of this first. Let's see that dA is dense in black space X. Okay, so we must show that the closure of dA is equal to X. Okay, this is to be dense. So we take in an F in X, okay, and we define ft as 1 over t integral 0 t ts f ds. So I don't know if you remember, but we have already used this in a theorem of the ones that we've seen before. Is part 2 of this theorem. We have that 0 t dsf ds is in the domain of A, and we know that A of this is ddf minus f. Okay, so let's see. So now going back to the proof, we have this definition of ft. So by 2 of the theorem that we saw, ft is in the domain of A because it is in the domain of A. Okay, this doesn't change anything. And also recall the part 1 of the theorem. We also here have exactly the same, but instead of h and t plus h, we will just take t as 0 and h as t, and we will have just the same. And we know that the limit when h goes to 0 will give us ttf. Okay, so by 1 we have that the limit ft when t goes to 0 plus this goes to t0f, because recall that here we have that the solution is ttf, but we changed where it says t by a 0, so this is t0f. But t0 is identity, so this actually is f. So the limit of ft when t goes to 0 plus is f. So we can say that f is the limit when n goes to infinity of sequences of functions, that all of these are included in dA, as we saw. Okay, where the f was chosen arbitrarily. It was any f. So okay, so this 1 over n is just we took before t, but now we to have a sequence of functions, we put 1 over n with n going to infinity, but 1 over n goes to 0, so we are having the same expression of the limit. T goes to 0. So finally, as f was chosen arbitrarily here, we have any f. So the closure of A is equal to x. Okay, this is in the closure, this is in x. Okay, so now we have that dA is density in x. So now we want to see the second part. This is that A is a closed operator. Okay, so A closed means that if we have a sequences of functions fn in the domain of A, okay, such that, well, fn converges to f and afn converges to g, then we will have that f is in the domain of A and a of f is equal to g. Okay, so that's what we want to see. Okay, so we have this. We have fn in the domain of A, fn converted to f, and afn converted to g. Okay, so now we will use again this magic theorem we've been using all the time. And now we will use part 3. TTF minus TSF is equal to the integral between t and s of d tau, af d tau, and also written in this form. We're going to use it using TTF, but here instead of t of s, we'll use it as t of 0, which is the identity, so here will be anything, and we will just have to change this s by 0. Okay, so by 3, we have that TTFN minus, well, T0, here comes a T0, but I will not put it, but it's just to see that we are applying theorem 3, that it's all legal. Fm, well, this is equal to T, here will come this ds, well, it's the 0, T is a Fn ds. Okay, this is for each n greater than 1 and t positive. Okay, now we will also use by theorem and all a theorem that we already proved that if we have a C0 semigroup and we have that T of S norm is less than equal than C E omega T. C is a constant. Okay, we already seen this. Okay, so now let's try to bound on this integral between 0 t ts af and ds minus the integral 0 t ts g ds. Okay, because we want to see um, um, the conversions between these two integrals. Okay, and then we will use that. So first we will bound this. So first we have the same limits here, so this could be one whole integral, and we will have ts here as common factor that can be put inside. Okay, so this will be less than equal, and we will put the norm inside. It's the integral 0 t of TS A F n minus G ds. Okay, and this will be less than equal, and now we will use s. Okay, and we will have z 0t a f n minus g ds. Okay, here should be not here, but inside the integral, then e e. Let's write it with more space. E omega t. Anyway, we will have that this is less than equal then the constant c a f n minus g, and then a term that sometimes that will depend of t. Okay, w, okay, minus 1 w, it doesn't matter because the thing here is that a f n converges to c. This is the thing. So this, when n goes to infinity, goes to 0. Okay, so we have that we can say that t is a fn ds converges to t always 0 t is g ds. Okay, and so we want to use this. We want to use it. How are we going to use it? In the following way. Let's make some room. So now we will have, if we put n goes to infinity, we have the t f minus f is equal to the integral 0 t of ds g ds. Why is that? Well, here it is. Now afn goes to converges to g, so here it is, and fn to f. We can divide this by t, okay, 1 over t, and take the limit. Let's put some limit here. T goes to 0. Okay, here should be another limit. 1 t goes to 0 plus. Okay, so first, what is this? What is the limit when t goes to 0 of ttf minus f over t? Just going back to the definition of C0 semigroup of a generator is exactly the limit when ttf minus f over t when t equals to 0. It's exactly that, af. So this is af. Let's write it in another place because here there isn't. So that is af. And what is this? What is the limit when t goes to 0 of 1 over t, this integral? Okay. Well, what do you think? We use it in the first part. 1 over t, this 1 over t integral tsf ds is f of t, and the limit when t goes to 0 of t is t0 of f equal to f. In this case, we have instead of f a g, so this is actually g. This is what we wanted to see. And of course, this also tells us that f is in the domain of A. That is the second thing that we wanted to see. This and this. Okay.